I want to talk briefly about another gas law called the ideal gas law, okay? The equation is PV equals nRT, all right? P is pressure in atmospheres, V is volume in liters, N is the number of moles, R is the gas constant. Remember we said we're going to use one constant, 0.082. That's the measure for the gas constant when we're using the units atmospheres, liters, moles, Kelvin. It's a different value if you were using kPAs. It's a different value if you were using PSIs. It's a different value if you're using millimeters or millimeters mercury. And T is in Kelvin. Okay, now, the ideal gas law is based on a concept of an ideal gas. This isn't a real gas. The gases most like an ideal gas are the noble gases, all right? Now, the ideal gas is really a model, and it's based on the kinetic molecular theory. Now, the kinetic molecular theory is saying gases are tiny, tiny particles, tiny atoms or tiny molecules or diatomic molecules, like hydrogen gas or oxygen, or a mixture of gases. But these are small particles. That's important because in an ideal gas, we're saying the volume of the particles of gas themselves are negligible compared to the overall volume of a gas. What that means is when we're talking about an ideal gas, okay, we're talking about the behavior of the gas, and those particles, okay, are so small compared to the overall volume of the gas, most of which is empty space, that the volume of the particle itself is negligible. Now, we're also saying, according to the kinetic molecular theory, that the particles of gas, like helium or hydrogen or oxygen, etc., particles of gas are in constant random motion. And pressure is collision of the particles with the wall of the container. So that means we can talk about the average kinetic energy. When we talk about that, what we're really saying is the average kinetic energy of the particles, the gas particles, is directly proportional to the Kelvin temperature. The Kelvin temperature is super important because we're talking about the whole idea of absolute zero. Absolute zero is the idea that there is absolutely no motion to the particles. So when we talk about absolute zero Kelvin, we mean particles of gas, or any particles, there would be absolutely no motion. Now, so the temperature then indicates how quickly gas particles are moving. So at high temperatures, gas move very quickly and hit the walls frequently. And at lower temperature, of course, they're slower and hit walls less frequently. So the temperature is a measure of the average kinetic energy, and pressure is collisions with the wall of a container. Now, with those collisions, we're saying the collisions of this ideal gas are elastic. What that means is there's no energy lost in the collision, either collisions with other particles or if collisions with the wall of the container. Now, this is all the basis for the ideal gas. Again, the ones that are closest are the noble gases, okay? However, there is no ideal gas, but we can actually make assumptions about real gases, because real gases behave similarly to ideal, okay? Similarly, but we can make these assumptions. All these gas laws, the combined gas law and what's called the ideal gas law, is based on this idea of an ideal gas that really doesn't exist. However, we do know that gases, any gas, air, oxygen, hydrogen, helium, any gas, okay, behaves enough like this ideal gas, especially at high temperatures and low pressures, that we can draw conclusions, we can draw these assumptions, which are basically these gas laws, like the ideal gas law. Now, but what we have to remember is this is based on the kinetic molecular theory, and it's based on a model for an ideal gas.